Hello everyone. I, Dr. Meenal Nerkar, welcome you all to this session on Quicksort. In this video, we are going to learn about Quicksort working, implementation, and analysis. Quicksort has basically three steps. One is pivot selection, then partitioning the element, and the third is recursion. Ah, in the first part, pivot selection, so basically pivot is an element to divide the array. Good pivot reduces the recursion depth, making the sorting faster. We can select first element, last element, random element, middle element, or the median of first, last, and middle element. Commonly, first and the last element is selected as a pivot element. Then the partition function. So the elements in the array are partitioned with respect to that of the pivot. So if you see over here, pivot is fixed here, and all the elements to the left of it are less, and all the elements to the right are greater than that of the pivot element. So in one partition call, it in every partition places one element exactly where it belongs. Once the elements are partitioned, then the recursion phase comes. We are applying the quicksort to the left subpart as well as the right subpart recursively, and this recursive division persists until each subarray contains only a single element. Once the subarrays consist of single elements, they are inherently sorted one. Now, so the same thing is pictorially represented over here. The first step in the algorithm is nothing but pivot selection. So over here, we are picking the first element as a pivot element. Then in the second phase, we are doing the partitioning. So partition function will place the pivot element at in such a way that it will all the elements to the left are less than that of the pivot, and all the elements to the right are greater than that of the pivot. Once this partition is done, we are applying recursively the quicksort process or the function to the left subpart and the right subpart of that particular array, and in this way this recursion continues until the subarray contains a single element. Now here it comes the explanation of the quicksort with the help of example. So if this is the array, we have selected the first element as the pivot element. Now we place the pivot element at its proper place with the help of that partition function. So now the left side subarray is containing all the elements. They are less than that of the 8, and all the elements which are greater than that of the 8 are placed in the right side subarray. So recursively we are applying again the quicksort function. So we are again picking the first element as a pivot element and then partitioning it. So left side subarray will contain two elements and right side is empty. Again apply the quicksort to this array as the size of the array is greater than 1. So now first element is acting as a pivot element, so it is placed at its proper place, and there is nothing in the left side subarray, and the right side subarray contains a single element. As it contains the single element, this means the recursion is stop over here, and we got the sorted output for the left side subarray, that is 2, 4, and 5. Then control will go to the right side subarray recursion, select the first element as a pivot element, and partition it. So after partitioning, we are getting left side subarray is containing element 9 and right side is containing element 22. So over here the control will come out of the right side recursion also. Once the left side as well as right side is completed, the output that we are getting is the sorted array, that is 2, 4, 5, 8, 9, 11, and 22. Now we will see how the partition function works. So over here, for the quick sort, we are passing three parameters: the array to be sorted, its lower bound, and its upper bound. Okay. So if there are some elements in the array, then we are giving call to the partition function. So control will come over here on the partition function. In this partition function, we are selecting the first element as a pivot element. So this start is pointing over here, and the pivot element is nothing but the 27. Okay. Now then we are making use of two pointers, pointer low and pointer high. Low is pointing to start plus 1 and high is pointing to the last element. Now over here, until our aim is to partition the given array in such a way that the pivot element is placed at its proper place. So for that, we need to compare the pivot element with all the elements in the given array. So for that comparison, we are running one while loop until there are some elements to be for the comparison. So if they are there, then we go on incrementing the low pointer until and unless we come across the element which is greater than that of the pivot element. Okay. And once that condition is satisfied, we will go to the other side and we go on decrementing the high pointer until and unless we come across the element which is less than that of the pivot element. Okay. Once we coming out of that, then we are simply checking whether the high and low crossed each other or not. If they have not crossed each other, we will simply swap the element stored at the a of low with the element stored at the a of high. Okay, so this is how this loop continues. So see over here, low is getting incremented, 53 is greater, so we will stop, control will go to the other side. High is now getting decremented, 43 is greater, so high is again decremented. Now as 89 is greater, so high is decremented, 14 is less, so over here it stopped decrementing, and array of low is getting swapped with the array of high, that is 14 and 53 will get swapped. So now after that high is decremented. No, now then control will come to the low part. The low pointer is incremented, 92 is greater, so it stop and control will go to the high side. Now it will compare the 62 with the 27 greater, so high is decremented, 18 is less, so now 92 and 18 are getting swapped. So in this way this particular loop continues, and this will continue until high and low crossed each other. So after some iterations, high and low crosses each other. So at this point we got the position of the pivot element. So a of high is getting swapped with the pivot element. So once this is getting swapped, what we can see is we found the position of the pivot element, that is 27, and if you observe, all the elements to the left are less and all the element to the right of it are greater than that of the pivot element. So this is how it continues. Once the partition is done, so that partition function is returning the position of the partitioning element, so that we have collected in the variable p, which is the split point. So we have to apply recursively the quick sort to the for the left side sub array, which is ranging from start to the partitioning position -1, and the right side sub array with the uh, which is ranging from p plus 1 to the end. So this is how the quick sort works. Now coming to the analysis part of the quick sort. So time and space complexity of the quick sort depends on the selection of the pivot, and the depth of the recursion basically depends on the selection of the pivot. Time complexity of the quick sort in best case is n log n, and the log n factor comes from the division step when partitions are balanced. At each partition step, Quicksort scans the elements to place them around the pivot, requiring big O of n amount of time. Therefore, the time complexity of the quicksort in best as well as average case is the depth of the recursion, which is nothing but log n multiplied by n, which is the amount of work done at every level. Now, coming to the worst case time complexity, this occurs when the pivot element that we picked is either the greatest element or the smallest element. If that is the and that case occurs if our input is sorted one. So uh, the pivot element will split the given array into the two part, out of which one is empty and the other is containing rest of the element. So that is why over here, if we observe, the depth of the recursion is going to be n, because the left side is containing zero element and the right side is containing rest of the elements. Okay. As the depth of the recursion is n, and at every level n numbers are there for the comparison, so the time complexity of the time complexity in worst case is coming out to be the quadratic one. uh, Now, coming to the space complexity of the quicksort. So quicksort has big O of log n space complexity for the call stack in the average case, but it can degrade to big O of n in the worst case, which with unbalanced partitions. It is generally considered an in place algorithm as it doesn't require significant additional space. So, to summarize, quicksort is a divide and conquer comparison based sorting algorithm that uses a pivot to partition an array into smaller sub arrays. The left and the right sub arrays are then sorted recursively. It can be easily parallelized for better performance. Quicksort has an average time complexity of big O of n log n, making it one of the most efficient sorting algorithm in practice. Thank you for watching.